Kia ora koutou. It's amazing to see this many people out on a cold Tuesday evening. Well done. The beer inducements must work. What I'm going to do is I'm going to talk through some work that we're doing. I'm very interactive. I'm going to throw questions your way, so you will have some things to do. And yeah, let's go. So the title is A Recipe for Quantifying the Impact of Prevention, Mixing Epidemiology, Economics, Big Data, Statistics and Simulations. So I'm an epidemiologist, public health medicine specialist, but sometimes called an epidemioeconomist. I blend epidemiology and economics these days. A lot of the work I did earlier in my career was linking census and mortality data, so I'm very familiar with government statistical agencies and that sort of thing. And a number of people there to acknowledge who are part of this talk. There's many, many more as well. Let's do it. So I have just arrived here at the University of Melbourne and set up this thing called the Populations Interventions Unit. And what I'm passionate about doing and trying to do more of and scale up internationally is to estimate how big an impact an intervention has. And that could be something like a drug, but mostly I'm thinking about prevention. And in stream one, it's doing sort of contemporary epidemiology stuff, causal inference methods, marginal structural models, that type of stuff with data behind you, the data we've already collected. But stream two is about going forward and simulating the future, whereby we actually try and work out what effect an intervention will have. And that's largely where I'm going to focus my talk today, and with the dissemination tool of interactive league tables, how you compare these interventions. And there's a heap of data that goes into this, and we'll just scratch some of the corners of where all that data comes from. So the structure of what I want to talk with you today about is as follows. Why do it? Rationale. How to do it. I'm going to give a very brief, one slide only overview of different modelling approaches, simulation, then I'm going to focus pretty much down on league tables. I'm going to walk, life tables, and then we'll walk through an example and then pull back to something we call VIVARIUM, which is our next generation simulation modelling. And then I'm going to talk about how we disseminate it with something called Australia-New Zealand-HILT, Health Interventions League Table. So that's what you're up for, and that's what we're going to do for the next 35, 40 minutes or so. So how does it all start? Well, it started because in 2006, I was thinking, what's the next thing will I do? And so I went and talked to this guy. This guy is the chief executive then of the Ministry of Health. Stephen McKernan's his name. And I said, Stephen, I'm an epidemiologist. I want to really help with policy. What can I do? I'm stylising the discussion enormously, obviously. And Stephen said, and this he did say, Stephen said, well, each year I have this problem. It's called the 100 manila folder problem. And basically on my desk in our boardroom, once a year, we have 100 manila folders with 100 different possible things that we could fund. And I can't compare between them. The drugs ones are done well by Pharmac, equivalent of your PBAC, where they do the, how much health gain you'll get, the cost, but the rest of it, they just can't compare. There's no way of comparing between those folders and what the health impact will be and what the cost will be to actually inform rational decision making. So that generated me getting enthusiastic about doing what we're doing now. So decision making in health is often idiosyncratic, ideological some may say. There's often a lack of ability to compare the health gains, health inequality impacts, costs across programs of disinvestment. I already said that drugs are well served by economic evaluation. Both Australia and New Zealand, and particularly the UK, lead the world in doing this type of analysis. But the approach in our view could be deepened and broadened, and good epidemiology is at the heart of it. You may have noticed this looks a lot like the health economists do. I'm very much coming from the angle of you create these models, you've got plumbing structure in there, and the flow through those water pipes are things like incidence rates, case fatality rates. There's a heap of epidemiology in there before you drop on your rewards like costs and things like that. What about decision-making criteria in health? So many of you don't work in the health area, but this would be a common type of framework if you're in the education sector or the justice sector. You need ways and frameworks. So things that people think about when they're doing decision-making include this long list here. What I'm interested in is those three. They're what we can quantify and put some more information on the table. I'm not dismissing the importance of politics and social values, but today we'll focus a bit more on the yellow stuff, which is more statistically orientated. So it's our contention and proposal that public health experts, let alone policymakers, are hopelessly unaware of the relative health impact of and cost impacts of public health interventions. There's a heap of work done on these things at the moment. Text messaging, apps. They're actually pretty good. They're pretty cost effective, but the size of health impact an intervention like this might have will be that much compared to something like taking the salt or reducing the salt in bread, because something like this has got a short timeline before it's obsolete. So that's sort of the game we're trying to play here, is trying to get people to understand their health impact. And whilst these are not the only criteria to consider in policy making, think of the list I just showed you on the previous slide, the ability to compare those health and cost effects should be a fundamental starting point. It's not the only thing, but it should be fundamental. Our proposal is that we should be routinely quantifying health and cost impacts to inform policy. It's not just policy, it's also future research directions. Because if you put some uncertainty intervals about that, you can see where the maximum uncertainty is propagating through your models, and that prioritises your next research, because you go and research something that has an influence on the overall decision. We won't do much on that, very little on that at all today, but just to make it clear, this is policy, but also other audiences. And we can bring them together into league tables, and importantly, Australasia is uniquely positioned internationally. We have hundreds now of interventions that have been analysed in nearly exactly, fairly comparably, and we can compare them. No other part of the world, no other corner of the world is that well positioned, and that will be the justification of some of the knowledge dissemination tools I present. And just to jump to the end, then I'll go back again, what I'm going to talk about is what everybody needs. Where's this cartoon from? Solarics. Yeah, where everybody needs a need. But I think everybody needs a league table. And so just to show you where we're going here, I'm going to focus largely on the mechanics of a life table. I've got to be careful when I say league table and life table. Julie, you'll pull me up if I get them mixed. Mechanics of a life table. But we're trying to estimate the effects for heaps of interventions. And this slide is showing what we call QALYs, quality adjusted life years, or HALYs, health adjusted life years, or averted disability adjusted life. For the purposes today, they are synonymous. And the wider the bar, the bigger the health impact. So you can see here at the top here, we've got a tax and subsidy package on foods. Big health gains all the way down to something like patient navigators who help the patient get through the cancer system to get their surgery and chemo. It's great for that person, but obviously there's not a lot of people that are going to benefit from that. And so what we're trying to do is show that big range of health gain. That's where we're going to end up in about 20 minutes when we start looking at these league tables. But how do we do it first? Well, we're going to walk through the general modelling approach and then go through some examples, and I'll be throwing questions out to you as we go along. And you may even be correcting me because there's quite a few numbers on the slides. Okay, this is a taxonomy. It's one from a paper that I co-wrote with some colleagues, and I've adapted a little bit for here. And there are axes and dimensions to this table. So you've got up here those that are cohorts. So this is where you model groups of people. So when you're modelling groups of people, you use things like averages, the average incidence rate, the average mortality rate. And then this part here, you're modelling individuals. So you actually take individuals and you stochastically or random walk them all the way through the model. Problem with this lot here, as most of you will know, is that takes a lot longer. There's a lot more simulations required there. Down here, we have no interaction with the environment and then interaction with the environment. So no interaction with the environment, we consider each group atomistically or each individual atomistically where they're not interacting with each other. The blue ones are the ones that I think warrant some mention. So very briefly, a decision tree. It's simply where you say some event we're going to do some treatment. We're going to give this person the red pill or the blue pill. And then we map out the things that happen to them with certain probabilities and we just roll the tree back. It is timeless. There's no aspect of time in there. We just work out the chance that they'll survive for a year, say, or that they will have a blood pressure lowering of 10 millimetres of mercury, or whatever it is. Work out all the probabilities, put some rewards on it on costs, well, that'll be the cost, and also rewards of life years gain, say, and just roll it back. Very simple, still quite useful, sort of thing that will be in algorithms in a computer-assisted decision-making tool, say in ICU, a lot of the time. Then there's something called comparative risk assessment. Very briefly, this is jargon from the global burden of disease. So Alan Lopez upstairs here with Chris Murray over in IHME, Institute of Health Metrics and Evaluation, Seattle. They've set up this massive descriptive epidemiology exercise. And part of that is where they say that the burden here, this number of disability-adjusted life years, is due to tobacco, is due to high salt, is due to whatever. But it's incredibly attributional. It just says the amount due to smoking if there had never been any smoking. So it's a very counterfactual, if the world had never had smoking type of analysis. But it's useful for ranking in some respects. Markov model, I assume this is teaching you guys how to suck eggs, but anyway, discrete time unit, and you basically spend time in a state. At the end of each time unit, be it a year or month, you get a chance to zoom off somewhere else or stay in your state. And that Markov model can have populations going through it, cohorts, or it can have individuals going through it with lots and lots of individuals, like a pinball machine game where they're just going through and through and through, and you're working out what happens as they have variation on their probabilities of transferring. The multi-state life table is what I'll be talking about mostly today. It kind of often uses Markov processes, but it hangs more off the life table, which we'll look at in a sec. Now that Markov model, as I said, can be used to propagate cohorts through, or can be used to propagate individuals through. Down here you've got things like system dynamics, where you're allowing for interaction with the environment. The number of fast food outlets in your neighbourhood might be determining your chance of moving from one BMI or body weight category to the next, and you get these feedback loops happening. There might be a policy lever over here, which is some tax on foods, and you can see where this goes. Data to support it is sometimes wanting. Over here, discrete event simulation is different. All these ones, or maybe not this one, but these ones here assume that there's regular time steps, right? Discrete event is different. We've done one where we look at the cancer care coordinators one, the one that was at the bottom of the slide. And so what you're saying there is I have 3 events that can happen next. The person dies of their colon cancer, or they get to surgery, or they get to chemo. And you just work out the probability of each event occurring, and then you randomly take them to whatever event is most likely, and you go to the next discrete event. That's why it's called discrete event simulation. It's a form of micro-simulation, so it's quite time-consuming, even when you've got high CPU power. And then agent-based simulation is an extension of that, and can be all sorts of variations. You really do need data at this point, and that's the major limitation in this area for agent-based simulation. Hugely attractive theoretically. We have an individual. They can hoon around in society. All these things can happen to them. But you quickly run out of the data to work out where they hoon to next. So, how do we do it? So this is the way that we generally do it in the programs that I've directed in New Zealand, the program that I'm setting up here. Is we do it as though we basically simulate a population. So we might take all of the New Zealand population, all of the Australian population, all of the Solomon Islands population, some base year, maybe 2016. And under business as usual, we work out how long they're going to live for, what diseases they're going to get, what quality of life they're going to get. So that's business as usual. And then we layer over the top of that some change, having got the business as usual model going, which takes a lot of work. We might say that there's some risk factor change due to the intervention. The BMI distribution just lifts slightly to the left, hopefully not to the right. Slightly to the left. Or we just slightly lower the blood pressure amongst those people who already had a blood pressure over 160, but some intervention around a risk factor. That will then go. So there you go. You've got your causes or your exposures or your treatments that go on to some risk factor, which then go on to change some disease incidences. So you'll then see some effect of that change in smoking or blood pressure or physical activity knocking on to some change in the disease incidence for those diseases associated with that risk factor. And then that, over time, will end up in different survival, different quality of life, and you can start working out the gains from that intervention by looking at changes in all-cause mortality rates. So you may not want to go through to all the way through to a combined metric like quality-adjusted life years, which combines mortality and morbidity, but you probably do, and so therefore you can go on to life years gained, health-adjusted life years, and as I said, QALYs and QALYs I'm going to use interchangeably and just use the term HALYs. As well as that, you can work out the life expectancy and the health-adjusted life expectancy. So life expectancy penalised, where you work out what the quality of life is as well as the amount of life, the health-adjusted life expectancy. And then you can layer over other rewards. So far, until this point in the slide, I've just been talking about the epidemiology, the things about the health part. But actually, once you've worked it out, you can say, well, they've now got colon cancer, so we'll give them the cost of having a colon cancer. And then when we do a screening evaluation where we don't let them get, well, we prevent someone getting colon cancer, that cost will drop. So you can work out changes over time in the health system cost. And then you can layer over that the productivity cost. This person is not actually going to contribute to the workforce. They're going to lose some income, which presumably loses the country some GDP for some period of time. So you can layer in the productivity costs. And then an area of obviously intense interest now is you can start layering in the environmental greenhouse gas effects. The simplest way in my area, it's not that simple, but the next step in my area is in dietary analyses. You can actually work out for each type of food what the greenhouse gas impact is, and as well as working out the health impacts of a dietary intervention, you can work out the effect on greenhouse gases, assuming that the food sector doesn't go and change how they produce it, which actually would be far more effective. But we can do it down here, assuming the food industry stays unchanged. All right, okay, show of hands time. How many people have played with life tables? I'm assuming many people, but there's a lot of hands not going up. Okay, so a life table, you would be familiar, you go off to the ABS website and you pull down a life table. And it looks a little bit like this, but there's some fundamental differences. Your normal life table, so when you listen to the news and they say the life expectancy in Australia is 84.2, it's a bullshit number. It is basically what the life expectancy would be if a person in 2006, a person managed to have the mortality rates that were seen in 2016 at all ages. So they get the mortality rate for infants, then for 2-year-olds, 3-year-olds, for the mortality rate seen in 2016. We call that a period life expectancy because it's bullshit, and it's just taking those mortality rates at this one point in time and pretending a cohort walked through that experience. A cohort life table is actually what happens when you unfold over time and you allow for changing mortality rates as they get older. So you've got both period and age effects happening in there, and therefore it's a cohort. Cohort life tables, often you go back to 1900 and you find a birth cohort and you can actually work it out because they should all now nearly be dead. Well, they should be by now. I'm going to be doing prospective life tables where we take the people now and we estimate what the future mortality rates will be by putting some trend on it based on past trends in the future, past trends and applying them out to the future. That's what this is. It's pretty simple, just a few steps. Every number in here underlined is an input, and the rest is worked out within the spreadsheet or within the life table, or if you do it in SAS or however you do it. So there's some mortality rates. These are mortality rates. We're going to start with 52-year-olds. We're picking 52 because they are the middle age of the 50 to 54 cohort. So we just bang it all onto 52-year-olds. And this is what happens to their mortality rate. And there's heaps and heaps more rows in here, and they get to 110, then we stop them there because if they're still alive, we kill them at that point. And then you just convert your mortality rate into a probability. Take it from an MX to a QX by just doing a bit of a flip there, which you guys will be familiar with. And then having done that, there's your starting population. There's 129,850 people, 50 to 54-year-olds in 2011 who are alive at that point. That's your starting cohort. And then each year you knock some of them off. So you multiply that by that to get the number of deaths. Then you work out the number of life years lived, which is in this case going to be the average of that number and that number. The number in this cycle and the number in that cycle is going to be slightly curvy like that as the cohort extinguishes, but a straight line is good enough over 1 year to give you the right average. And then you can work out a number of interesting things like the life expectancy. The life expectancy is just going to be the sum of the life years lived down here all over the number of people alive at the beginning. That's what that formula is saying. Sum of all that stuff all over the starting population there. And here we see that for somebody who, for a cohort at the age of 52, their remaining life expectancy on average, the expectation is another 34.2 odd years. Now this is where we start layering in the quality of life stuff. So these are what we call PYLDs, which stands for prevalent years of life with disability. And in this particular instance, they come from a separate study, like a burden of disease study. Australia has the burden of disease studies done by AIHW, Australian Institute of Health and Welfare, but you could go to the IHME website and get the global ones. There's different sources. And what it is you basically work out all the diseases that could be happening amongst 52-year-olds, and they're all given some form of disability, and you work out the total years of life lived with disability for that group. Having worked out that number, you divide it by the number of people in there, and bingo, you've got some form of morbidity measure. So in this case, we can see it's 11.2% or 0.1122, which means you've lost just over 90% of your quality of life on average by the time you're 52. I'm 52, bugger. And then it gets worse and worse by the time you get older and older, so you've lost about 2/3 of your quality of life. So that's the adjustment part. So having got this part here, you can work out your QALYs, which is now just going to penalise. You're going to take 1 minus that because that's your loss. So that that's left is 88 point blah, 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 88. and then you multiply that by your life years here, and you get these numbers, and bingo, you get your health-adjusted life years. Down here, there's the total amount there. There's the total number of life years left to live. This is the total number of health-adjusted life years for that cohort. And you can also use the sum of all that over the starting number to get your expected health-adjusted life expectancy, which is 26.93 compared to 34.19. That's how a life table works. None of it's hard. It's just several steps in flying it through. Now, we want to start simulating stuff. So here's a really simple example where we say, imagine an intervention that lowers the all-cause mortality rate by 5%. And what happens here is each one of these numbers here is just 5% less than that number up there. That's the only difference between, on the inputs, between this panel up here and this panel down here. The rest of the maths all works across exactly the same except for that 5% reduction in each of the incidence rates here. Let's go to some results. So what you can see here, this is the total number of person years lived amongst the cohort, and that's the number of person years that would be lived if they had a 5% reduction in mortality rate. They gain this many 58,000 odd life years. They gain 40 odd thousand health adjusted life years. They gain 0.45 in life expectancy, the difference between here and here. Now notice this here, this is just over a 1% gain in life expectancy, which is considerably less than the 5% reduction in mortality rates, because remember, all mortality is going up exponentially, which if you turn it in survival curve looks, I'll do it your way, turn it in survival curve looks like that. It's quite hard to keep nudging out that survival curve when your mortality rates are going up exponentially. So the gains in life expectancy won't be as much as the converse of, or the mirror image of, the reduction in the mortality rate. It's just the limit on the system. And there you go, got 0.31 gains in health-adjusted life expectancy. That's it. It's pretty simple. That's why people like me do it, because I can do it with spreadsheets. Our spreadsheet models, as just an aside, that do this stuff for heaps of diseases, they're up to 32 megabytes now, which is getting a bit embarrassing. So we're now moving over to Python. I'll get to that soon. Now, most interventions, you can't really just link them straight up to a mortality rate reduction. You need to take them through the diseases. So smoking is going to hit some diseases, and we want to model changes in those disease incidences. So we need to actually now think about, well, what about a simple intervention that had a 5% reduction in coronary heart disease incidence? You can't just do it in this life table. You actually need to go to a subsidiary life table for coronary heart disease itself and then get some numbers and bring them back. And this is how it works. Same type of structure, but now you've got different inputs. You've got an input of an incidence rate that varies by age, a case fatality rate, and a disability rate by age. The disability rate is pretty much the same as that PYLD or the morbidity or the burden of disease one from the previous slide. Having got these inputs and starting off here with the number of diseased people, so to get all this data, we actually have to do a lot of work. Cancer is quite easy because you've often got a good cancer registry in a high-income country like Australia or New Zealand, and you can go and get those number of cases and you can work out your incidence rate and they're followed up and you can get the excess mortality rate. Not too hard. Something like coronary heart disease, which is still a big killer, it's actually quite hard to do that because when did they develop coronary heart disease? Was it when they were hospitalised or when they had their first trick? You have to develop algorithms for working that out. Anyway, so quite a lot of work to get the primary data. And then you might say have an incidence rate, case fatality rate, prevalence, and a duration. Those all work together mathematically, and you only need 3 of them to specify the system, but they've got to be coherent. So we do a whole lot of tweaking of those things to make sure the inputs are coherent. That's as much as I'll say. It's a bit like the back of a kitchen in the restaurant. You don't want to know much more detail. It gets pretty messy. Having got those inputs, though, and this is why, when I get to the slide, we're increasingly trying to work with the Institute of Health Metrics and Evaluation, because they've got $600 million from Bill Gates with a bunch of machine learning to work this parameter out for every damn country that moves. Well, the countries don't move, but every age, sex, in all countries. So we're trying to harness that big data in our next phase. Anyway, back to what we want. Having put these things for coronary heart disease, you've got your business as usual. The only difference between this panel and this panel is a 5% reduction in incidence rates. Everything else is the same on the inputs, but it just flows through. So this is also bullshit. They typically start with 1,000 people in these life tables because what we want out of here is not absolute numbers. We just want to get changes in mortality rate and changes in morbidity rate. And if we make the somewhat brave, but doesn't matter too much, assumption that the diseases are independent. We can do this for several diseases in parallel and just sum up their impacts onto the overall mortality rate and take them back to the main life table. So what we're really interested in here is, having gone all the way through here, these are the differences in mortality risk for the intervention compared to BAU, and the differences in morbidity. So we've worked out in this subsidiary disease life table the differences in those morbidity risks and mortality risks. And then it's quite a simple exercise to take these differences, and there they are there. There's a difference in incidence, the difference in mortality, which is, this is the input, that's an output of that change in incidence there. These are the actual values, and this is over age, and the coronary heart disease prevalence. So you can see for 5% reduction in incidence, you get a small, modest reduction in CHD mortality and somewhat of a reduction in CHD. These are the things we're capturing here, the difference in height between the solid and dotted lines. And you just go and pop them back in to your main life table here. So here we go, there's the business as usual, there's the 5% reduction all-cause mortality rate at all ages. We've already done this one. Now for the 5% reduction in coronary heart disease incidence, what we're doing is, see these numbers here? That's the mortality rate in the intervention arm. I'm in a feedback zone. They're very similar to up here under BAU, because it's going to take a while for that change in incidence to flow through into changes in prevalence, which with constant case fatality will eventually flow through to changes in mortality rates. So it takes, there are lags in here, which is what you want, because that's the way the world is. But you see these numbers here? They're now somewhat lower than the numbers up there because of the influence of lower coronary heart disease incidence on a subsidiary life table. And then you just flow it all the way across the right in the same way that we did for BAU and the simple mortality one. So there we go. There's the changes. Flows on to slightly more life years lived. So you see 233 is just a little bit bigger than 220 there for the 110-year-olds, those who made it all that way through. And there's the number of person years lived now, having taken the count of the cohort. So you can see that this was our gain from the 5% reduction in mortality. We gained that many life years. So that number is that minus that. Now we gain 9,000 or so, because it's just working on coronary heart disease incidence. When I say just coronary heart disease incidence, is a big cause of burden of incidence and death. So it's still, 15 to 20% of that number, but it ain't anywhere near as big as that. And then you get your gain here in the health-adjusted life years. So you can see this is how we start to estimate the impacts of those interventions, by quantifying these HALI gains, life year gains, health-adjusted life year gain, life expectancy gains, and health-adjusted life expectancy gains. So that's it. In concept term, that's how we do these multi-state life tables. I just showed you one disease, but imagine 16, 20 of them in parallel, each coming back up to feed into the all-cause mortality life table. And that's what it looks like. It's a bathtub. Basically, the incidence is the water going into the bath. The plug hole is the case fatality rate, draining it out. And the height of the water is the prevalence. That's all we're doing. We're just playing in bathtubs. Sometimes we put a kid in the bathtub and they kick the water out, or the water comes back, and that's recurrence or relapse. Extending the metaphor perhaps too far. As people interested in prevention, we're largely playing with the tap. So we're reducing incidence to reduce the inflow to the bathtub in 16, if it's tobacco, 16 parallel tobacco-related diseases that feed back up into the main life table. But we could actually play with the plug hole if we're having an intervention that changed the mortality rate as well, but normally we're playing with the tap. In a little bit more detail, the concept of what we're doing is on this rather busy graphic. I've shown you the main life table in here, so you've got an idea about how these work. A lot of work to specify the business as usual. We just talked about some of the parameters. There's that DISSEMINATIng thing that calibrates or makes sure that the incidence, case fatality, mortality, prevalence, duration, and one I've lost, there's 6 of them, are all coherent because there's a mathematical system in there. And then you've got your intervention inputs. Now the intervention coming here is that change in disease instance. We sometimes we bring that in through there from the parallel or subsidiary disease life tables. To get your inputs into the disease life tables, this is where we can get all this machinery here working in a relatively routine manner. But each time you do a new intervention, you've got more work to do in here. So here's some examples to give you an idea. This is where the work happens once you've got your engine room going. So there's many types of interventions. So for example, primary prevention changes risk factors. We were talking about that before. But you might also have prevention change in disease incidence directly. So like a bowel cancer screening program will reduce the polyps, take the polyps out of the colon, and also cause early detection. So it's both changing incidence as well as detecting disease earlier. So you've got to have a bespoke upfront intervention model to do that. I'll talk about another one there. So this is nice and simple. So if you had a reducing pain intervention, you might say it reduces morbidity by 20%. That's quite easy. Just change those disability rates. Often very imprecise though, or uncertain. Another one is you're doing a tax intervention. You need to have a whole lot of price elasticities in there to determine how much a risk factor changes. So there's a lot of work at that bespoke end there. These are the outputs. We've talked about those here, and there's a heap of these inputs. I'm not going to go through them all. We're just going to pick a couple of examples in the next 10 minutes. So we'll just do the one example of cost data. And because I'm still think I'm a Kiwi, I'm sort of halfway between being a Kiwi and an Australian. Not quite sure which side of the Tasman I'm on some days. We have this thing called the integrated data infrastructure, which is not a hip-hop song, it's just an integrated data infrastructure. And what it is, it's quite extraordinary. It's Scandinavia in the South Pacific. It's routine data all brought together in one place. So this makes many Australians' eyes start to weep at this point. So in this data set, you have all the health data. It's all linked up to the tax data, the education data, all at the individual level. It's pretty cool. And it's also linked to a whole lot of economic business data sets. A couple of things we can do with this. First one is for the health system cost. We don't even need to use, we just use the health cost in here, but we use it in the data lab because it's updated routinely. We basically can see over time who gets their disease when, and when they get their disease, we flick on the switch for having got coronary heart disease or having got chronic lung disease or IHD or whatever it is, ischemic heart disease here. And then they may hoon along at being prevalent, and then we'll flick on another switch if in their year of death and they're about to die of that disease. Basically, all those things go into covariates on a massive, boring old OLS. This is an OLS regression model run over the entire New Zealand population with everybody disaggregated by time, sex, ethnicity, all the diseases, all the disease comorbidity combinations. And then you can spit out at the end of these really useful numbers. This is the cost by first year of diagnosis, prevalent case, and if you're in the last year of life and dying of lung cancer, ditto colorectal cancer. You can cast your eye down there. So it makes sense because the green bars are less in width, because cost of being prevalent is less than in your first year of diagnosis or if you're in your year of death. But those, in a Markov model or a multistate life table, which is macro simulation, it's got the memoryless assumption in it, but you still know when the people go in and when they go out. So you can actually give them different costs on entry, incidence cost, and on exit, which is death cost. And then every other year they're in that state, they get the prevalent cost. So that's just one example of the type of data we put in there that's pretty cool. But it gets even cooler. We're doing it right now at the moment, whereby we're using that same massive OLS, but rather than using the total health expenditure for each individual, we actually pull in their tax data. And so we've got their income, and we can see how their income changes when they develop disease and when they don't, allowing for comorbidities. We are optimistic that this will be a major jump forward internationally in what we can do here, and basically get those productivity costs as you develop disease, put the productivity costs in simulation model. Why does this matter? When I was last speaking to the Minister of Health in New Zealand, and we're talking about all the health stuff, he's pretty excited. I'll show you, the last slide today is what he wanted for his talks with the food industry. When we say we've got the productivity costs, his eyes come out. Why? Because he can now go to cabinet table and he can argue with the Minister of Finance about the impact of doing something in the health sector on the overall economy. And all of a sudden, he, in this case, has got far more traction. So these productivity costs and being able to put them into the model in a comparable way is quite important and quite innovative. Enough of that. Right, what I'm going to do is I'm actually not going to walk through three, I'm going to go two. I'm going to do a tobacco tax example and then eradication. So let's walk through this. So you know how the mechanics work now. I'm going to give you some results so you can sort of see what it looks like. And this is based on a paper that we put out there in 2015. It was kind of a big moment for us. It was where we got our first model really working properly, and this is what we leverage off a lot these days. And so the methods, you know a lot of the methods already, but here's a bit of a bullet point summary. includes those following 16 diseases. Pop quiz question time. Why are those 3 diseases in green? Melanoma, thyroid, and endometrial cancer. Sorry? I will start picking on people. I'll start giving you some clues. We put every disease into those 16 ones that had association of tobacco with disease incidence such that it affected at least 0.5% of the total burden. Sorry? Reduced, thank you. We put those ones are actually lower. Endometrial cancer is an estrogenic cancer. Tobacco is anti-estrogenic. You get lower endometrial cancer rates if you smoke. Thyroid cancer is a bit similar. We think it's anti-estrogenic. Melanoma is just a bizarre disease. It's an immunological, it's just about really not a cancer. But anyway, just to make the point that we're not trying to be biased here, we put the diseases in that are associated with smoking, even those that are protective. We're not saying that there's enough protection there that we're going to change the health messages to the population and go out there and start smoking. They make bugger all difference compared to some of the big things in there like respiratory disease, heart disease, yada, yada, yada. Julie is taking bets on how many times I say yada, yada, and I was determined to not say it. I was determined not to say it today, and I just slipped up. All right, we grabbed the all-cause mortality rate from the Statistical New Zealand life tables, and my colleague and I wrote a book about the history of mortality in New Zealand from Captain Cook all the way through. And if you draw a long curve, the mortality rates are going down by 1.75%. You can see the numbers, that's where it comes from. We used DISSEMINATIng and all that stuff I've talked about. We took the morbidity from the, you know what they are now, the YLDs from the New Zealand burden disease. You've seen the cost. So you get an idea of what's going on here. This is what it looks like. Highly stylistic graph. On the y-axis is the adult smoking prevalence. Now, when you're doing a model like this, you not only need to do your BAU on the epidemiology, but you also need to do the BAU on the risk factor. So we did a heap of work on this and worked out what we think under steady state conditions of about the same tobacco control intensity as witnessed in the last 50 years, what the future tobacco prevalence will be, which is that line there. Okay, so this is what we think the tobacco prevalence is going to look like as time unfolds here. Now, the blue line is business as usual. Pop quiz, why does it take a kink there? Sorry? No. Good try, though. I'll give you a clue. We take all the population alive in 2011 and we simulate them through. It's a closed cohort. We assume they all take up smoking by the age of 20 and no more uptake after that. That's the turning point, because at that point beyond there, so it's a closed cohort. You could call that a limitation. What we're doing, we call it a strength, because every model's done the same way, the same closed cohort, and it means you're not following the population up indefinitely for thousands of years until that cohort is extinguished. The red line is what we think will happen to the prevalence if we put a tobacco tax. In this case, it's 10% per annum increase in the excise tax from 2011 to 2031, which is not pie in the sky, because actually that's exactly what New Zealand's done and on the books to 2020. Whether it'll keep going is another point, but this is not a pie in the sky intervention, it's a real one. The purple line is what would have happened if the Minister of Health, Minister of Finance and Prime Minister in 2011 had been one Tony Blakely. We'd have just eradicated it. That's the Tony Blakely line, but we'll use that. And so what you can see here is that the QALYs gained, or the HALYs gained, between these two lines is 275,000. It's a big number. It's a bit like the distance to the sun. It doesn't need too much, so you need some context. So the way that we do that is say, well, what is the total envelope of health gain you could get from getting rid of tobacco, which is why we've got the purple eradication line. If we eradicated tobacco and then allowed for the time lags of the effects to wear off, so it's not that comparative risk assessment attributable one, it's the simulate the forward one, we get this many. And at this point you think, actually that's not too bad. This one intervention, if you divide that by that plus that, it's about 18% of all theoretically achievable health gain can be achieved by this one intervention of tobacco. That's not bad. It's not bad. That's the good news. Here's the news that you don't like showing your tobacco control advocate mates. This is the timing of those health gains. It takes 60 odd years, 70 odd years for the health gains to peak. Now, a couple of things here. Green is non-Māori, red is Māori. They happen to be about the same because Māori smoke more, have higher disease rates from smoking, and so even though they're only 15% of the population, it just so happens that it's about the same when you come to the HALYs, which means it's a highly inequality reducing intervention, by the way. And these ones here are the dotted lines where you discount. So each year into the future, it's worth 3% less, 3% less, 3% less. So by the time you go 100 years out, these lines are much less than here. Nevertheless, so the point here is that those health gains are decades away into the future. Why? There's several reasons. Oh yeah, an economist would like to discount those gains, but yeah, they have to discount the cost, and we'll see that in a sec. But why is it decades until we get the health gain?
The damage has already been done.
Damage has already been done. Yep, next one.
Genetic effect on children.
No, this is just the one cohort going through, so it's just those people alive at the time. Who's most price sensitive? Young people. How far away from their NCDs? Decades. They've got to get into their 60s, 70s, and in the future in their 80s and 90s by the time they're living longer under the assumptions in the models. So they're a long way away from it. Who smokes more? Young people. So this model is very skewed towards the younger population. So it's going to take decades to realise these health gains, which, you know, if you actually compared that to my cancer control evaluation, that would look big. So it depends on the scale, because this one's really big in its totality. But you do have to wait a while. And this is a common issue, I won't call it a problem, a common issue with prevention is it takes a while to get those returns. A classic example where it's not so long to wait is the colon cancer screening, because you're whipping out those polyps and you're getting in there and changing that disease process quite near where it might have killed you or caused morbidity. Right, so that's the health gains. Here's the health costs for you, sir. So they are discounted there as well. So you can see that they are slightly closer in time. They're not quite as many decades out because those costs are happening when you've got the disease before you die of it, but the Halley gains are a bit more driven by when you die. Now, pop quiz time. This is the cost saving. So at this point, it's costing you money. Why is it costing society money? Why does it go beneath that axis there? Exactly. So we use what we call unrelated health costs. There's a lot of argument about economists, when you're doing an evaluation like this, do you only count the health costs that are close to you? I'm treating this person's breast cancer, I'm only going to count the cost of that breast cancer event. But actually, by saving people's lives, they live longer, and you should account, and we do. Now, the cost of people living longer in this model is sort of way down here, and the cost of preventing future emissions is way up here, and this is just the net of those two forces. But at this particular point on the graph, it's costing you more because you're keeping people alive longer. Bummer. I'll let you decide whether you think that's important or not. But as a statistical audience, I'm sure you're interested in that. Right, so that was all done in 32 megabyte Excel spreadsheets, which are prone to error, and believe me, I've had to publish some retractions, not retractions, that's the whole paper, errors, and it wasn't very nice. Hey, George. George up the back there used to work with us in New Zealand on some of this stuff, and we had a particular boo-boo on one once, which wasn't much fun. So that's not the only motivation for doing it, but we're now working to bring it all into a Python environment, and this is what we're doing. We're basically saying we've got a strong track record of doing this in New Zealand. So the stuff I led in New Zealand, we actually stole the models from here, the ACE Prevention Group, Teo Voss, Rob Carter, and heaps of others. A lot of our people out at Deakin use these models. But there's both sides of the Tasman have been doing lots of interventions. We're now collaborating with the Institute of Health Metrics and Evaluation, and we're building these next generation multi-state life tables in Python. Why? Because the idea here is once we're in that environment, we can pull down all these GBD parameters to parameterize those BAU models and start doing multiple countries at the same time. At least for the more routine part of it, the intervention could still be quite bespoke. That's where we're putting the stuff up, and we're currently getting on the way with the tobacco. Now, I'm conscious I've probably spoken too long, so you're going to get a very brief overview of the life tables. 5 more minutes, Judy? No? Yep, okay. So basically, there's about 400 plus, maybe 500 actually, this has been updated already today, of evaluations we consider comparable enough in Australia and New Zealand to do this with. Those 68 New Zealand ones, they're for the overall population. We've done a lot of stuff by ethnicity and age, so there's a lot of heterogeneity analysis there, so it explodes out to another 400 when you drill down to populations, subpopulations. We've built this thing in R Shinny App, so I'm presuming many of you have encountered these types of tools before. And what you can do as the user is determine what domains, so there's about 11 domains there of diet, physical activity, and then each intervention domain, you can select those interventions. You can choose the currency. So we transfer all the dollars between Australia and New Zealand and into US currency to get that comparability. You can pick the publication year, and we'll go into that today, and you can decide which year to have it based on inflation. And these are the things you can look at. You can look at the total population per 1,000 population and cost effectiveness plane. Very briefly, here's the total population. So they're the same ones I showed you in that slide with the LORICs before. So everybody needs a league table. And so these are the same ones. So taxation on tobacco, this is, they're colour-coded, that's pink is for a tobacco intervention. 25% of salt and processed foods. Now this is an unfair comparison. That's New Zealand, that's an Australian one. There's a key difference between Australia and New Zealand. You guys have 6 times as many people as us, and this is the total QALYs. So one of the next things we do is we say, well, actually let's make these demographically adjusted, so it's per 1,000 in the total population, so we've got a fair comparison across place, but also over time as populations change in their size. And you can see here that salt intervention goes up to being the top one because it is really quite effective per 1,000 of the population. This is the type of thing you can start doing. There are hundreds of evaluations in here that we're showing to policymakers so that they can start getting a sense and start solving or at least addressing the 100 Manila folder problem. We use these things called cost effectiveness planes. How many people have used a cost effectiveness plane before? Okay, very briefly, because you're statisticians and you're smart, it works like this. On the x-axis is the health gain in QALYs. On the y-axis is the cost here. And we plot all these interventions. So the first one showing is reducing tobacco outlets. It gets all this health gain and it saves you money because the intervention itself doesn't cost too much other than the political will. Seriously, that's the cost, but it was not in our costing, and it saves future hospitalisation. So it's down here in what we call the southeast quadrant. Boom. Health gain and cost saving. Here are the other interventions. I've just blown it up a bit for you. This is the CT screening of smokers. Use CT screening of smokers, heavy smokers, to detect lung cancer early. This line here is called the willingness to pay line of about $50,000 per quality adjusted life year gain. That's what a rational, well, it's what, no, it's not fair. It depends how much money you've got each year, but that's about the amount of money as a rule of thumb a society will spend to get a quality. It's up here, which means it's costing more than $50,000 per quality, so don't do it. Not until the technology gets that much better or something like that, or cheaper mainly. That's a screening program for Helicobacter pylori. It's a bug in the stomach. It actually causes the vast majority of stomach cancer, and you can actually screen for it and then treat it with antibiotics, and it's quite effective. That is something that's going to cause waves. It was already causing waves in New Zealand, because whilst it costs money, it's still cost effective because it's beneath that line. And you can see, you can look at these things and see all the cost effectiveness plane. I'm going to finish up on this slide. So the minister came along and opened a symposium with us last year, and he said, look, I'm talking to the food industry. Ministers love talking to the food industry. They don't necessarily like regulating the food industry. But anyway, he was talking to the food industry, and he said, give me some ideas on which interventions are going to have the biggest impact, and particularly inequality reduction, which we won't get to today. So we created this league table for him and went along and showed it all to him. We don't know what's happened. It goes behind closed doors, and he works with the tobacco and the food industry. Whoops. But you can see here, if you tax sugar, I don't just mean sugary drinks. I mean sugar across the whole food chain. All the sugar in New Zealand comes into one factory. You could do it. Wouldn't be hard. And tax it at 40 cents per 100 grams, you get this amount of health gain. That's big, remember? So it was about 270,000 for the tobacco tax. This is 450,000. And you can cast your eye down that. You can see all the ranges here. Now, I've always put a couple in here that people know and trust. There's your colorectal cancer screening program, which is a really good thing to do. But look at how much bigger some of these nutritional ones could be. And there's your tobacco tax, 10% to 2025, not to 2031. Also a really good thing to do. And look at some of these food things. Remember, everybody eats, not everybody smokes. So something that might have a small effect in the dietary space per individual can sum up to being a lot. So I think that's where we'll stop. What I've tried to do is give you a bit of a sense of why, how, and how to disseminate this stuff. I hope it's been useful for you. If you have an interest in this area, I'm interested. Come and talk to me. Kia ora koutou.
Thank you very much, Tony. When I said you'll tell us everything, I didn't realise you'd take me literally. I'm sure there are plenty of questions out there. Who would like to pitch the first one? Yes.
How do you go with explaining the uncertainty? Because I assume that's what the sponsor at the last one. How do you go with explaining that to politicians?
Yeah, good. I even put some slides in for you. I knew you'd ask that question. Here's a good one. We recently did an analysis on e-cigarettes. Quite good health gain, but look, huge uncertainty. Whereas something like the tobacco tax still has a lot of uncertainty, but it's there. How do we do it? well, you guys probably know more about this than me, but if you drill down into a Bayesian perspective on this, it's still the expected value that's the most useful for the policymaker. But I think most policymakers want to know about that uncertainty. Because you may find policymakers and politicians who are very nervous about doing this because this is getting close to zero. We couldn't find any instance where that was less than zero apart from young kids and older people. I won't go and explain it now. So how do we convey that to policymakers? It's always a tricky discussion. The league table up there at the moment doesn't have those uncertainty intervals automatically, but it will do soon, is what we're working on at the moment. So I don't have a complete answer for your question other than we do talk about it.
Yes.
I worked on case mix funding, and that was modelled on the US figures with percentages. Australia then implemented actual time and costs, but then there were also the severity of a young person responds much quicker to a disease and a treatment than an older person. So as that was implemented, there was a drift of as the costs became more effective. Now, how do you cope with that in the modelling?
So how do we cope with the fact that different people cost, by age you cost different amounts?
Yeah.
Okay, so there's a lot in this question, so I'll pick out some bullet points. So the first thing is those costs I showed you that we put in the model, they are the excess costs compared to somebody without any of the disease in the model. So your control, if you like, the person who's healthy is actually probably got other disease not in the model, so that person's going up, and it's the excess cost for somebody with lung cancer compared to somebody the same age. Yeah, so hidden in that, what we call it the Joe citizen or the healthy citizen cost down here. It's not that they're healthy, it's just that they've got other diseases, things that make them see the health system other than the 16 tobacco or the 21 related, dietary related diseases. So they're in there and we're putting the excess cost on it. We're trying to put the cost in there that we think is getting close to the counterfactual cost if they hadn't got that disease, other things held constant. So I think that largely answers your question. The next bullet point I'd say is that we had the cost for the year of diagnosis and the year of death if you die of that disease, and prevalence, so that we can capture the timing effects. So if we delay death, you're going to push that end of life cost out, which if you're a discounter, where's our economist? If you're discounting, that will make a little bit of difference. So I think they're the two key things to raise there. But we do work quite hard on it.
One question just in relation to the tobacco specifically. What's your source for the elasticity of demand?
Yeah, good one.
That's got a fair bit of uncertainty.
Yeah, the answer is 0.47, which is the best New Zealand estimate. We've actually just been looking at this. Was Anchor here? No, but we're looking at this today. And the estimates of so price elasticity, if you put the device back up by 1%, the elasticity is the response to it. So when I say negative 0.47, it means if you put the price of tobacco up by 1%, overall consumption goes down by 0.47%. And what everybody does, ourselves included, is you then say half of that is due to people quitting, the prevalence is half of that, and the other half is due to people smoking fewer cigarettes. Now that number that we got of the 0.47 is slightly different from the global estimate that everybody uses of 0.4 because we had some specific New Zealand data. So that's where it came from. What we don't know is this: here's your total household budget, and you're a smoker, right? As that price of tobacco goes up, you're going to keep spending more and more, and at some point you're going to hit some hard limits on your housing and stuff. You're not going to have that much discretionary income. At that point, you would theorise the price elasticity will start to get bigger, which in this case means more negative, because you're hitting up against those limits. We haven't seen that yet, and we would go and look at cocaine, heroin, cannabis. Those price elasticities don't tend to vary across the price range, curiously enough. So hopefully that's given you an answer to your question.
The uncertainty comes
Yep.
from that data.
Yep, the uncertainty there. And we tend to err on the side of over-specifying uncertainty. We don't run away from it. So we put quite wide uncertainty about these. So we take the price elasticities and other parameters from overseas. We'll often double the size of that when we bring it into New Zealand in 2011 because the study was done in 1985, yada, yada, yada. Damn it again.
Question here.
If somebody's interested in collaborating or helping out with this project, what's the best way to do that?
Just come and see me.
Okay.
Yeah. Drop me an email. Yeah.
developed versus developing countries?
Yeah. So a classic example of that is HPV vaccination. So HPV is the virus that causes the majority of cervical cancer, but also penile, anal, and vulval cancer as well to some extent. And the cost of that intervention varies a lot between countries until Gates came along with Gavi and other things, and they lowered that cost. So the cost is often the biggest variation between countries in that context. But if we think back to tobacco now, in our work with IHME, it's not just that we want to use their data, is that we're going to use their new methods, which not only look at whether you're a smoker now or not, but how many pack years you've smoked. So somewhere like Laos might be earlier in the tobacco epidemic, people have been smoking longer. So the epidemiology may vary between the countries too, and we're really interested in 2 to 3 years' time once we get there to see how much difference allowing for that phasing of the tobacco. So there's heaps of types of reasons, but normally speaking, something like salt, if you know what the cardiovascular disease rate, particularly the stroke rates are, you can pretty easily back of the envelope go between countries on that one.
Could you use historical case studies to try to scale these benefits?
I thought you were going to say validate.
No, I'm curious, for example, how these line up against mandatory seatbelt laws.
So what do you mean by scale these benefits?
Well, so you said, for example, that 275,000 QALYs was a lot.
Oh, I see.
Well, is it? Who knows, right?
Oh,
So
okay.
what?
Okay, so what you're saying is I've done a league table where evaluations done in the last 10 years or so, but what you're saying is maybe we could work out what some intervention impacts were for something done in the 70s like seatbelt laws. Yeah, that'd be a great addition to the league table. I don't know the studies that have done that, but it's a good idea. But we don't have that type of historical stuff. What I thought you were going to say is, can you validate your models? Can you show that your model replicates what happened with a past intervention? That's really hard in prevention.
You can answer that question now if you like.
It's really, it's really hard in prevention because just about everything in public health has multiple causes and multiple policies, and it's really hard to pull out those predictive validation exercises, which we'd love to do. I thought that's what you're going to ask.
So I guess I'm just thinking through what would happen if you had one intervention that was possible at one point in time and then another intervention with stem cell therapy.
Okay, so I hear two questions in there. The first one is we can model packages of interventions. You've got several things happening at the same time. There's very few studies that look at multiple interventions at the same time to give you exact relative risk for doing everything at once, but we have various tricks for doing that. Remember, you've got an envelope, so each time you take away some of the burden, there's a bit left over, so you can layer them in like that. But what you're talking about is whereby the technology changes and you've got something new. Now this is really, if you're in the treatment space, this gets quite hard because your comparator has also changed over that time. And so, for example, if you've got a stem cell treatment for, I don't know, kids' leukemia, and you compare it to evaluation done 20 years ago, the treatments done 20 years ago, the baseline's changed, the types of normal chemotherapy used. So the stem cell, if it was done back here, may have been more effective because there was more headroom to gain, whereas it's done out here, it'll be less. And we're seeing that with interventions that now don't look as cost effective as they used to because the background has changed. And a good example of that, just following on from your lead, is the Lancet published this week, I think, last week, a review of all the aspirin studies, and it's looking like aspirin doesn't prevent cardiovascular disease as much as it used to, and I mean that. It's not just that the evidence was wrong in the past, as the epidemiology has changed, so you do get these things happening. And the last example I'll give you is whereby an intervention no longer becomes politically acceptable or just societally acceptable. So in that league table, we had criteria for including everything, but we then threw 3 out. And one of them was because Teo, who did the ACE prevention, came from South Africa, where circumcision was a good way of preventing HIV, and then modelled it for the Australian population. But we decided circumcision probably wasn't an acceptable intervention in Australia. So there's quite a lot of nuance around that, and a lot of it's to do with the comparator and who you're comparing against and the time, which matters a lot more for treatment than public health. But even the public health, like that aspirin CVD one, things change over time.
There's time for one more question. Yes.
Sorry, you may have mentioned it, but how do you pick which interventions to model and also which diseases?
Oh, yeah. All right, best question for last. Picking the interventions to model is a really tricky issue. If you want to get, I'm going to exaggerate to make my point. If you want to get funded by the NHMRC, they may well like you to be teamed up with VIC Health and other agencies, and they'll want you to do interventions that they consider more feasible and doable. So it will be a program to do some of this. It won't necessarily be a program to take the nicotine out of tobacco or to do a radical tax program. So you've got quite a lot of tension there. So what we do, and I'm not saying it's right, is we try to do a 50-50 thing. We'll pick about 50% of our interventions which we consider are doable in the next 3 to 5 years' time. They might be a mass media campaign, they might be something like that. But we'll also pick the other 50% which are stretch. We're academics, we're in an ivory tower, let's use that. So we'll pick interventions that people don't think can be done now, but may well be feasible in 20 years' time and may actually change the agenda. So looking at a radical reduction in the number of tobacco outlets. Back in this space here, we tend to convene advisory groups and work with them. They'll suggest 20 interventions. We'll go away and do the homework on those. We'll come back to them and say, well, look, only 10 are viable because the evidence on the other 10 is crap. It's not worth modelling it. The uncertainty interval is going to be so wide, it's not even worth doing it. And we go for a process like that. Yeah, so there's a bit of an art to this. And it makes a lot of difference because what's in your league table depends on what previous researchers chose to do. And on that league table, you'll notice that the dietary interventions in Australia and the physical activity ones have a lot less health gain than you might expect because they were working in an environment that were looking at small interventions. So there's what I call researcher endogeneity there and what's selected to be done.
On that note, please welcome, please join me in thanking Tony for a excellent talk.
Thanks, Brian.